National Space Academy have been working with PPG to help schools across the UK engage in chemistry in the classroom using the context of space. And this partnership has inspired us to delve deeper into colour and find out why it's so important to space. Colour is everywhere. It can affect how we feel, how things taste, it can influence what we buy, and even tell us what to do. Colour is personal. Today, I'm going to show you how colour and space fit together. Light is made up of different colours, and these different colours have different wavelengths. Red has the longest wavelength, while violet has the shortest. But where do we get light from? Our biggest and most important source of light is the sun. Back in the 1660s, Sir Isaac Newton let a very thin stream of sunlight into his dark room and split it with a prism. Light is refracted when it enters the prism, and each colour is refracted, or made to change direction, by a different amount. This means that the light leaving the prism is spread out into its different colours, a process called dispersion. So Newton found out that sunlight is actually made up of red, orange, yellow, green, blue, indigo and violet. Sunlight isn't yellow at all, it's actually white. You can refract light yourself at home with a CD. There are these tiny ridges in the surface of the CD that are reflecting the light in different directions. I also have these cool glasses that split up the light. Here, have a look. It also happens with bubbles. When white light from the sun shines through the film of bubbles, the light is reflected and dispersed, splitting white light into its different wavelengths, revealing all the colours of the rainbow. This is how rainbows work. We get rainbows when it rains because the raindrops scatter the light when it shines through them. So we get colour from light, but how do we know what colour objects are? Historically, rockets are mostly white. To find out why, let's take a look at why objects are different colours. When light hits an object, that object absorbs some of the light and reflects the rest of it. Some objects reflect more of a certain wavelength of light than others. That's why you see a certain colour. This lobster is red. That means it's reflecting the red wavelength back at us into our eyes to something called the retina. Your retinas are home to two types of photoreceptor cells, rods and cones. These specialised cells convert light into signals that are sent to the brain. There are three types of cones: red, green and blue. Each type responds to different wavelengths of light. When different combinations of cones are activated, you see the world in colour. This toy rocket is reflecting all the colours back into my eye, so I can see the rocket is white. But why are rockets white? Rockets all look quite similar, and they are all long and pointy, and they're normally all white too. This is useful to keep track of rockets against the blackness of space, but there's another reason. White absorbs the least amount of heat, which is really important for keeping things cool in the extreme temperatures of space. This is also why spacesuits are white. But not all of them are. Most spacesuits are white, just like rockets. Now this helps them stand out against the black of space and also helps protect them from the heat. But not all spacesuits are white. Some spacesuits are orange, like this one here. Now this isn't to do with heat, but actually to help us find them. This is called international orange, and if an astronaut was to land in the middle of nowhere, it'd stick out so we can see where they are. So colour helps us identify where something is, and also what something is. Scientists can use colour to tell them information. We can use universal indicator to tell us how acidic or how alkaline something is. It's measured using a pH scale that goes from 0 to 14. pH is an important measurement. We can use it to measure water quality and doctors can use it to diagnose medical conditions. Water is neutral, which means it should have a pH of about 7. And if we pop our universal indicator in there, it should turn green. Let's give it a try. I'm going to pop a good few drops of universal indicator into our water. And in a second, we'll give it a good stir. So as we can see, our water is nice and neutral on our pH scale, but to change it to orange, just like our spacesuits, we're going to need to add something acidic. And today, we're going to use vinegar, just like you'd put on your fish and chips at home. So again, we'll add a good glug of vinegar in there. We'll give it a good stir, and we'll see if we can get that nice orange colour. So we can see it's now turned this orangey red colour because we've added an acid to the universal indicator. Now you can make your own universal indicator at home, and I'm going to show you how today using a red cabbage. So to complete your experiment at home, you're going to need a few things. You'll need a chopping board and a knife. Now remember to get an adult to help you with that part. You'll also need your red cabbage and some filter paper, or you could use a sieve from your kitchen. You'll need a couple of beakers, a kettle, and to test it out, you'll need something acidic and something that's alkaline. We're going to look at using our vinegar from earlier on and bicarbonate of soda. The first thing you'll need to do is chop your cabbage up into quarters. Now remember, you'll need a grown-up to help with this. Once you've chopped it into quarters, you can put 3 of them to one side, as we're only going to need 1 for our experiment. We're now going to need to chop that 1/4 up into really small pieces. If you've got a blender at home, you can use that to chop it up into even smaller pieces. Next up, you're going to want to put some of your chopped cabbage into your container and then add in some boiling water. Now, you may need a grown-up to help you with this part too. Be very careful. Once you've added your water, you'll need to let that sit for about 20 minutes. Once you've waited 20 minutes, you'll need to take your filter paper or your sieve and place that in your second container. You're then going to need to pour all of that water through your filter paper or sieve to separate the water and the cabbage. Now be careful, as your water may still be hot. Red cabbage contains a natural pH indicator that changes colour according to the acidity of the solution that's been added to it. So if we add an acid, we should get a pinky red colour. When it's neutral, it should be this lovely purple colour. And if we add an alkaline, we should see a greenish blue colour. Once you've filtered your indicator, you'll need to dilute a little bit of it into some water. Next, we're going to add our bicarbonate of soda to our first beaker. So as we can see, it's turned it this nice blue colour, which tells us it's an alkaline. We're now going to see what happens when we add an acid into this beaker using the vinegar. So as we can see, it's turned it this nice pinky reddy colour, which tells us this is definitely an acid. And that makes me think, why is Mars red? Mars is often known as the red planet. But why is it that colour? Mars is covered in dust that mainly contains iron. Now that iron has reacted with the oxygen in Mars's atmosphere to create iron oxide or rust, which means the red planet is actually more orange. The colour of each planet is determined by what they're made up of. and in some instances how their atmospheres absorb and reflect light from the sun. Uranus and Neptune, for example, appear to us as blue because methane gas reflects blue light. Things out in space have some amazing colours, but we actually look at space in black and white, because black and white cameras give scientists the most amount of information. Space telescopes have red, green and blue filters measuring different wavelengths. They combine them to get a true colour image, or what you'd see if your eyes were as powerful as the Hubble Space Telescope. They also use colour to see different elements, like hydrogen, carbon and oxygen, and use colour to see their presence in an image. So colours are used to send information. The Hubble Space Telescope can also see in non-visible light, like infrared. Scientists use it to see through clouds of dust so they can see stars behind and in nebulas. And we can use it here on Earth to see through things like bin bags. All objects on Earth emit IR radiation in the form of heat. This can be detected by electronic sensors such as those using night vision goggles and infrared cameras. Now the brighter colours you're seeing represent the warmer temperatures, whilst the darker colours, a bit like my cold fingers, represent the much cooler temperatures. Something we don't need to use infrared to see are the northern lights. So why are the northern lights green? And why do they happen in the first place? It starts with the sun, which gives off solar wind. Electrically charged particles travel 93 million miles towards Earth, and then the Earth's magnetic field typically deflects 98% of those charged particles. But that remaining 2% are drawn towards the magnetic north and south poles, which is why we get the northern and southern lights. The charged particles then hit the atoms and molecules in the Earth's atmosphere, getting them all excited, causing them to glow. Just like in this plasma ball, the electrode in the centre gives off an electric current, like the sun gives off solar wind. Inside the ball is a gas representing the Earth's atmosphere. When the current goes through the gas, it causes it to glow. The colour of the northern lights and the colour of the plasma ball depend on which molecules the charged particles hit. The most common colour we see in the northern lights is green. We get green because the charged particles are hitting oxygen atoms. Our plasma ball contains nitrogen, which is why we get this pink. Although astronauts can see the northern lights from the International Space Station, they often say they miss the colour green. And that's because colour and emotion are connected. Just like when we say we're feeling blue. Green reminds us of nature, which is something the astronauts don't really get to enjoy when on the ISS because they're surrounded by all this machinery and the black of space. Astronauts do get to see the Earth from space, but they mainly see blue. They call it the blue marble. Being out in nature can really change your mood. Having a look round at the different colours of green and the blue of the sky. So next time you're out, why not have a look and see what colours you can spot? A question I get asked a lot is why is the sky blue? So to find out, we're going to do an experiment that you can do at home as well. For this experiment, you're going to need a glass of water, a little bit of milk, a spoon and a torch. The first thing we're going to do is add just a couple of drops of milk into our water. Now I find it easier to pop my milk onto a spoon and then stir it in. So when we add the milk to the water, the milk particles are suspended. And this means that when we pass a light through it, like our torch, we're able to see that light beam because the light is scattered. Try holding your torch at different angles to see if you can spot any colours. Now, in comparison to this, if we hold our torch up to a regular glass of water, we can see that nothing's there. And that's because there are no gases or particles inside to scatter the light. Now, similar to this, when the sun shines down on the Earth, its light is scattered through our atmosphere. Gases and particles in the atmosphere scatter the light in lots of different directions. Now, blue light is scattered more because it travels in shorter and smaller wavelengths. And this is why we see the sky as blue. So, why is colour important when we're talking about space? Well, it's light from the sun that brings colour to our Earth. It gives us rainbows and the northern lights. And colour can even help astronauts be found and launch them into space. Looking out into space, we see the colours of the planets, and telescopes like Hubble allow us to see the beauty of nebulas and galaxies. And then we look back at Earth, the blue marble, the blue dot. And both you and I know there's more to colour than what's on the surface. To find out more about the work we've been doing with PPG to offer Chemistry Masterclasses, check out nationalspaceacademy.org/PPG.